So how much carbon you add to the iron is the critical component. When you add just a small amount of carbon, the material is very ductile. So for example, I have here a bobby pin and I have a paper clip. The paper clip has a very small amount of carbon in it, okay? And so when I heat this material up, so when I can take this material and I can bend it around, and it's very malleable, right? And so that's a low carbon iron alloy, all right? It has about 0.2%, so it's down in that wrought iron phase. Now what's interesting is if you heat this material up and you quench it, so I'm going to heat it up very hot, I'm going to turn it into austenite, all right? And then I quench it, all right? When I do that, I actually quench it so fast that the carbon doesn't have a chance to move around. Now there's only a little tiny bit of carbon in here, so it's not critical. But the iron actually no longer has that face-centered cubic phase. It actually has a body-centered tetragonal phase, and it makes it harder. And so you can see when I go to bend it, this part is very hard, and so it doesn't want to bend, but the stuff that wasn't quenched is still soft, and so it bends. So I can make the material very hard, but it's not terribly brittle. And so this material can be very useful. For example, if you wanted to make a sharpened edge on a scythe when you're harvesting wheat. All right, but this is very low carbon, and it doesn't get as strong as it possibly could. Now, if I take a bobby pin, it has higher carbon. It has about 0.7% carbon. And that carbon moves it all the way into the steel regime. So this is actually a form of steel. All right. Now what's interesting about this is that this is still ductile. It's harder to bend, all right, than your paper clip, but it is still ductile. All right. And when I take this now and I quench it, all right, I heat it up, I make my austenite, I quench it. I've now made a phase called martensite. And that martensite is that body-centered tetragonal phase I was talking about before. This is also very hard. Now, the difference is that I had a lot more carbon, and that carbon didn't know where to go. So it got stuck in there, and it induces a lot more strain. So this material becomes brittle and will break, all right? And so that was the challenge, right, is that I varied the amount of carbon. I could take it from something that would be hard, but still have some ductility, to something that becomes even harder, but is now very brittle, all right? So when they were trying to figure this out early on, they didn't understand what was going on with the phases, but they knew they could manipulate the properties of this material. And that's what made iron and steel so valuable. So what we've been talking about is a heat treatment, and that's where the trade aspect of working with iron and steel came into play. And so understanding how this worked was critical. If you do a heated up, for example, if I take the same piece of steel and I now heat it up, all right, and I slow cool it, okay, then I no longer form the martensite. I allow the carbon to form around where it wants to do, and the material actually maintains its ductility. So the idea was I could make it harder if I quenched it. So if I did this process right, and I heated it up really hot, and then I quenched it, I could make it very hard, but we know now this is very brittle. Then what they would do is they would make it very hard and brittle, but then they would do a process called tempering. Tempering meant I come back again and I heat it up gently and I let it slow cool again. Now I've retained some of that hardness, but I've restored the ductility of the material. It's no longer brittle, all right? So that ability to manipulate iron was critical in its development as a material.